after your talk. Yeah. Okay, please.
Great. Many thanks for the kind words. Can you see my screen okay?
Yeah, no problem.
And can you and can you see my second slide?
Correct. We can see your second slide.
Okay. One of the things I'm going to talk about a thread of research that's developed over the past 7 years, and it goes back to 2015 when the European Commission asked Aaron Leverett, Richard Clayton and me to examine what the Internet of Things implied for safety. Because the European Union regulates safety of all sorts of devices. There's several dozen verticals, children's toys, railway signals, cars, all sorts of things, where the European Union is by default the world's regulator, because Washington is too gridlocked to make any decisions, and nowhere else is really big enough to matter yet. And this creates a problem, because what happens once you start getting software and everything? So we produced a report for them in 2016, which appeared in public at WISE 2017. And the conclusion of our report is that once there's software everywhere, safety and security become very seriously entangled. Now, in fact, the two are the same in most languages spoken in the European Union. Sicurezza, seguridad, sûreté, Sicherheit. And so the problem facing the European Commission and its galaxy of regulators is, how do you update safety regulation and safety regulators to cope? Now, this means that we have to start looking at safety engineering as well as security engineering. And safety engineering is much more fragmented. Rather than having a single safety engineering profession, you've got people who do safety engineering for cars, for railway signals, for medical devices, and so on. And we looked at 3 specific case studies where we had some expertise at cars, at medical devices, and at electrotechnical equipment such as substations. Now, in the case of cars, cars were really unsafe for the first 70 years or so that they were on sale, until in the 1960s, Ralph Nader's book, Unsafe at Any Speed, caused a scandal in America and led the government to set up the National Highways Transportation and Safety Administration. In the European Union, we've got a separate story. In the 1970s, the Product Liability Directive stopped manufacturers disclaiming liability for goods. And then there are sectoral laws such as a directive on type approval for cars and many other things that have appeared over the years. And there's over 20 European Union agencies plus some United Nations agencies in play here. So what happens once cars start to get hacked? Well, in 2011, one of the prize-winning papers at Auckland was a paper by Yoshi Kono and others on Car Shark, which was a way of hacking cars if you one time had physical access to them. And that was treated as an academic curiosity by the industry, because if you could somehow get a device into a car, then was it surprising that you could control it? Now, industry's complacency was shattered in 2015 when Charlie Miller and Chris Valashek hacked a Jeep Cherokee over the air, because Chrysler was putting a network called Uconnect into their cars, which are just Sprint, and it wasn't authenticated. So if you could guess the IP address of a car, you could go into its systems and you could read data and you could start to control it. So if we got your IP address, we could hack and control your car. And they did a demo by taking over a car that was being driven by a journalist, and they slowed it down until it was going so slowly that they could engage the auto park system, and then they run it off the road, as you can see in the photo here. And all of a sudden, people cared. And Chrysler had to recall over 1 million vehicles for a software fix. And as the software fix involved getting cars into the garage and reflashing the memory in some chips, it cost them a lot of money. It cost them over $1 billion. So all of a sudden, CEOs in the car industry started to sit up and pay attention. And here's another example of car hacking. Some of you may recognize the guy on the left. He used to be the chief executive of Volkswagen. And the picture on the right shows what happened to his share price when it came out that he had been hacking the software in Volkswagen cars so that the car would detect when it was being subjected to an emissions test, and it would then throttle back the engine so that it would pass the emissions test. But then when it wasn't being tested, this would vanish, and it turned out that cars were emitting much more nitrogen oxide than the law allowed. And this brings home that it's not just external hackers who form part of the threat model here. The threat model includes the executives in the car industry itself. And I personally have a 10-year-old Mercedes that we bought secondhand, and we're now part of a class action to try and get several £1,000s back from Mercedes because Mercedes were doing this too. In fact, most of the cars in the car vendors in the car industry were hacking their emissions controls. So you find pervasive dishonesty in some industries, which involves the vendors and goes right up to the top level. Here's another example of widespread use of computers in safety critical systems. This is the intensive care unit at Swansea General Hospital. Some photographs taken by my friend and colleague Harold Thimbleby. How many CPUs can you see in this picture? Right, this is what happens to you if you're in a car crash. If the car computer goes haywire, you end up attached to all these machines which monitor your vital signs and may pump drugs into you. Well, here's a hint. As you can see, there's quite a lot of them. And as you recover from your car crash, you might be depending on 40 or 50 CPUs and their associated software, just as you are depending on 40 or 50 CPUs and their associated software while you're driving your car along. So what goes wrong? Well, here's an example. Here are half a dozen, 7 infusion pumps that are used in Swansea in the General Hospital. And if you look at them, you see that the controls are all different. The keyboards are laid out differently. And so if you're a nurse, you've got a potential problem because the buttons that you have to press on different units are different. It's as if you're trying to drive a car, where some cars have got the accelerator on the right of the brake pedal and others have got the accelerator on the left of the brake pedal, something that actually happened in the 1930s, but the car industry got rid of. But if you look here, you'll see that the two bodyguard pumps, one of them has got a keyboard that goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So you've got to use the keys 2 to increase the dose and 0 to decrease the dose. Whereas the other one called Bodyguard 545, you've got to press 5 to increase the dose and 0 to decrease the dose, right? So the controls are quite different, and it's easy to make mistakes. And Harold showed that hospital safety usability failures kill about 2,000 people in the UK, which is about the same as road accidents. And the biggest culprit are in fact the infusion pumps. Now, Harold took an interest in this. His father unfortunately died in such an accident. But for the most part, these accidents aren't very salient to medics and hospital administrators. Because in a big hospital like the one we have in Cambridge, well, there's 240 general hospitals in Britain. So you expect that Edinburgh's hospital in Cambridge is about killing 8 people a year. And that means it's less than 1 a month. And that means that safety usability failures of infusion pumps are about number 40 or number 50 in the list of causes of avoidable death in hospitals. So nobody pays attention to it. And in any case, people who die as a result of these failures are usually pretty sick anyway. The mistake may not be noticed, or if it's noticed, it won't be reported. Or if it is reported, the tendency is to blame the nurse rather than to blame the poor design. And that's one of the reasons that things go wrong. Safety usability is ignored because the incentives are wrong. And that's why airplanes are safer than hospitals, because plane crashes are very public things and people care about them. And lots of people die at once, so they become front page news. Unlike in safety usability, where people die one at a time in hospitals. Now, the interesting thing is that attacks are very much harder to ignore. And back in 2015, Kevin Fu of the University of Michigan did a Wi-Fi tampering demo showing that he could hack into the Hospira Symbake infusion pump, and he could use that to get into the hospital network. And this led to a huge big panic, and the FDA actually blacklisted that infusion pump. And Kevin then turned around and said, well, what about the 200 other brands of infusion pump that are unsafe? And the FDA said, oh, well, we don't want to do anything about that. 2017 saw the recall of 450,000 pacemakers sold by the company St. Jude. And this is actually quite serious, because if you've got a pacemaker, it's typically implanted surgically in your shoulder. And if they're going to dig into that to change the pacemaker or to reflash the memory or to change the battery or whatever, it involves a surgical procedure under local anesthetic. And they have to have a cardiologist there in case your heart starts misbehaving. So that costs several $1,000s for the operation. So again, this is something like the Chrysler recall with total costs in the billions of dollars. And so the question for us is, what should Europe do about this? And in the case of medical devices, the medical device directives were in fact revised. And from last year, the new directives require post-market surveillance, per device risk management, ergonomic design. And one of the regulations says that for devices that incorporate software, the software shall be developed in accordance with the state of the art, taking into account the principles of development, lifecycle, risk management, including information security, verification, and validation. And 18.8 says devices shall be designed and manufactured in such a way as to protect as far as possible against unauthorized access that could hamper the device from functioning as intended. Now, this still isn't perfect because there's wriggle room around economics and network security assumptions and so on. Is the hospital network trusted or isn't it? But it's a huge improvement. And this is one of the mandates that's going to be driving investment in cybersecurity over the next 10 years. Because if you're a medical device maker, you want your medical device to be sellable in Europe as well as in the USA. And the European Medicines Agency, which used to be in London, it's now moved to Amsterdam because of Brexit, is in a position to hold medical device makers to account in a way that the FDA never used to. To be honest, the FDA has been improving, because after Biden got elected, the FDA hired Kevin Fu for a year as an advisor, and he built up a cybersecurity team, which is now able to do proper testing in America as well. But the ground was broken in Europe by the move towards this medical device directive. The third thing that we looked at was industrial control systems. About a decade ago, I had a research student who was interested in electricity substations and was funded by ABB. And so this is something that we got to know a bit about. Now, in an electricity substation, you've got a 40-year life cycle. You have got communications protocols such as DNP3 that don't support authentication. And an electricity substation is basically a LAN with about 200 devices on it. Things that computer scientists understand, like network workstations, and things that heavy electrical engineers understand, such as big transformers and reclosers and so on. Now, these protocols don't support authentication because they didn't used to need it. But all of a sudden, 20 years ago, people started doing IP networking because it was cheaper. And that meant that suddenly anybody who knows a sensor's IP address can read from it. And anybody who knows an actuator's IP address, then you can activate it. And we discovered 10 years ago that the only practical defense was to reperimeterize. It just takes too long to change protocols in an industry where people are very standards bound. And so what people do nowadays is they have a firewall at the boundary between their substation and the big bad internet. And that keeps out bad things, and it encrypts the communications to your network control center. And that is something that we replace every 5 years. But the interesting thing that we discovered when doing this work is that all of a sudden people were starting to build smart grids. And then arose the issue of smart meters, which are being put in people's homes. And then there's the question of who controls the off switch, because if you suddenly put into every one of Britain's 28 million households a meter which can be remotely turned off, right, so that if somebody doesn't pay your bill, you could put them on a prepayment tariff, then what happens if Vladimir Putin just hacks all the smart meters in Britain and turns off all the electricity? That's a serious big deal. And we pointed this out as a risk 10 years ago, and some work has been done on that, although things still aren't perfect everywhere. Anyway, so what did we learn? Broad questions that come out of our reports include: who will investigate incidents and to whom will they be reported? How do you embed responsible disclosure? There was one scandal a few years ago where researchers at the University of Birmingham in England and the University of Nijmegen in Holland discovered a flaw with Volkswagen's remote key entry, and Volkswagen threatened to sue them and to make them shut up. Now, this caused them to have to censor part of their paper at Usenix Security, but thankfully the University of Birmingham won the law case against Volkswagen, and so the flaws were in due course disclosed. But some industries, like the car industry, don't have the responsible disclosure culture that we have in mainstream computer science. And that's something that I will come back to later. Next question is, how do we bring safety engineers and security engineers together? We have different cultures. We go to different conferences. We speak different languages. And as I mentioned, there's not one profession of safety engineers, but about 20 or 30. The nuclear safety people and the aircraft safety people have quite different cultures and backgrounds. Will regulators all need security engineers? Well, the problem is that in Brussels, many of the regulators don't even have any engineers at all. It's used to be the case that medical device makers, regulators, didn't have any software engineers, indeed any electronic engineers at all. And that's the thing that you have to fix first. And again, how do you prevent abusive lock-in? Because tech is plagued by monopolies, large and small, and so is healthcare. And if the healthcare industry gets together with the software industry, you can expect in the long run to see more concentration, higher costs, inflationary bottlenecks, taxpayers and patients being ripped off. So the recommendations that we come out with included requiring vendors to certify that products could be patched if need be, requiring a secure development lifecycle with vulnerability management, a cybersecurity advice body for European safety regulators, a duty to report breaches and vulnerabilities to safety regulators and users, and extending product liability to services. And roughly speaking, we've got the first three of those of those recommendations, but not the last two yet. But there's one thing that we realized after we had done this exercise. Richard Clayton and I were at Schloss Dagstuhl for another event, and we said, well, you know, what did we learn from all this? And one thing that we just realized over a beer was this, that there are basically two types of secure device. There are phones and laptops which you patch monthly, but which you make obsolete quickly so that you don't have to support 100 different models. And then there are things like cars and medical devices, which we test to death before release, but we don't connect them to the internet, and we almost never patch them. So what happens to your software support costs now that we're starting to connect all sorts of durable goods to the internet? And we'll presumably have to patch them, right? We've seen this already in the medical device side of things, and in cars too. If somebody comes up with an over-the-air attack on your car, you have to patch it, as Chrysler did. So what's this going to do to your costs of the industry? So here's the trilemma. If you go for the standard safety lifecycle, you get no patching, and you get safety and sustainability. But if you go online, you get hacked. And if you go for the standard security lifecycle, you get patching, which keeps you safe, but you break safety certification. And if you do patching and you redo safety certification with current methods, then maintenance costs can be sky high. So how can you get safety, security, and sustainability at the same time? This is the trilemma. Which of these two do you want to choose? So if you look, for example, at the economics of the vehicle life cycle, vehicle lifetimes in Europe have about doubled in 20 years, and cars now last about 15 years on average before being scrapped or exported. And the or exported bit is important because many of the cars in Africa are cars that used to be on the roads in Europe or in Japan or in Singapore. And then when they got to a certain age, they were put on a ship and exported to Africa. The vehicle makers we were talking to 5 years ago wanted to say, scrap every car after 6 years and buy a new one. Because if you're a Mercedes, your business model is that you sell rich people a 3-year lease on a new car, and you sell slightly rich people a 3-year lease on a Mercedes approved used car. But if you're someone like me with a 10-year-old Mercedes, then they see you just as a sucker who pays through the nose for expensive spare parts. So from Mercedes's point of view, they'd be delighted if all cars were scrapped after 6 years. But here's the problem. The embedded CO2 cost of a car often exceeds its lifetime fuel burn. Right? A typical Mercedes might last for 300,000 miles. That's why I bought one, right? And if suddenly it has to be scrapped after 6 years, then that's no good. And what about Africa, where most vehicles are imported secondhand? If the European Union allowed us to go to safety rules which say that all cars have to be scrapped after 6 years, then we double the CO2 emissions from road transport, and we can't have that. There's always a cartoon. And here's the XKCD. The car's making a funny noise. Can you have a look? Sure, just pop the hood. Oh, the hood latch is also broken. Okay, just pull up to that big pit and push the car in. We'll go get a new one. Right? That's how we deal with computers. You can't do that with cars. There's too much embedded CO2. And this brings us to the economics of dependability. Now, one of the things that we've been studying at Cambridge and elsewhere now for the last 20 years is the economics of security. And we realized there that complex socio-technical systems often fail because of poor incentives. If Alice guards a system but Bob pays the cost of failure, you can expect trouble. Now, security economics explains platform security problems, the network effects, lock them in and then get it right by version 3, the patching cycle. It explains liability games, and it explains an awful lot else that we used to treat as just bad luck. And the same principles apply to safety as well. And safety and security are becoming entangled. So the economics of dependability becomes ever more important. So one of the things that you can do once you've got reasonable economic models is to use these to give advice to policymakers. And so one of the things that our report was used for was to push to improve the software lifecycle of products with digital components. And the European Commission made 3 attempts at this, and they succeeded on the 3rd attempt, which was Directive 2019/771, the Directive on Sales of Goods. And this says that buyers of goods with digital elements are entitled to necessary updates for 2 years or for longer if this is a reasonable expectation of the customer. And the trader has a burden of proof in the first 2 years. But what do we mean by a reasonable expectation of the customer? Well, in cars, we've already got European regulations which say that a car vendor must make spare parts available for 10 years after the last instance of the car leaves the showroom. So that means you have to maintain software for 30 years. Roughly speaking, that's 3 years R&D while the car is being designed and tested, 7 years while it's being sold in the showrooms, and 10 years after that. With domestic appliances, it's 10 years spares obligation plus store life, so it might be 15. Medical devices might be something similar. Phones, this is new. The European Union is now saying that phones must be maintained for 5 years. Apple does this already, but some of the Android vendors are going to have a hard time, and they're complaining that some of the cheaper Android phones will vanish from the European market. I don't personally believe that, but you expect device makers to say that because that's lobbying. Electricity substations don't fall under consumer law, but there you're talking about maintaining software for maybe 40 years. And the World Economic Forum now has a circular vision for electronics. So what does this mean for research? Well, if the durable goods we're designing today are going to be still working in 2060, then things are going to have to change. And our trade, computer science, is about managing complexity. And so the history goes through high-level languages, their types, their objects, tools like GitHub, Jenkins, Coverity. And so what we have to ask ourselves is what else will be needed for sustainable computing once we've got software in just about everything. So how should this affect our research and teaching? Well, since 2016-17, I've been teaching safety and security engineering together in the same course for first-year undergraduates, and that's all available online since the pandemic, so you can go and look at the lectures. We also started to look at what we can do to make the tool chain more sustainable. For example, can we stop compiler writers opening up timing channels? TLS was proven to be secure 20 years ago by Larry Paulson, yet there's a bug report about once a year. Why? Because somebody came along with some new compiler hack, which noticed the padding instructions that were being put in the crypto libraries to cause the crypto to run in constant time. And all of a sudden you've got a timing channel, and then Adam Laurie's got to get out of bed at 3 in the morning and patch open SSL, right? So what can you do about that? Well, we did some work on better ways to communicate intent. If you Google for the paper, what you get is what you see. You can see the result that we did there. And now for the rest of my talk, I'm going to talk about the effects of machine learning, because one of the things that happened after we did our work for the European Commission is that we got invited to talk at Bosch's annual research conference, and they sponsored one of my students, Ilya Shamailov, to look at machine vision. And this got us deeply engaged with adversarial machine learning, because deep neural networks are much better at doing computer vision than anything else. Since the deep neural network revolution in 2011, 2012, where two teams in Switzerland and in Canada suddenly discovered that you could, if you made a neural network big enough and trained it with enough examples, you could do vision really, really well. And the following year, a couple of teams discovered that you could easily produce adversarial examples because gradient descent methods could find you ways of tweaking an image slightly so that the classifier gave the wrong result. And so we then found, for example, a team of researchers in Israel showing that you could confuse machine vision systems in cars by projecting funny patterns onto a motorway bridge. And are you really worried about this? Well, we thought not, because if you're prepared to send a drone flying along behind a car to do an attack on it, you don't project something onto a motorway bridge. You shoot a Hellfire missile into it. Come on. So the right response might be fragility rather than robustness, so that the machine vision system gets to know that it's under attack. But how would you go about doing that? Well, let's remember what we know about adversarial inputs. There have been a lot of talks about this in the last 5 or 6 years, but here's a classic example. If you look at the standard images that are used for testing machine vision systems, there's an image of a bird on the left. And you can tweak that with a just noticeable difference, which I've hugely amplified in this slide so that you can see, but these are basically these significant bit tweaks. And so the tweaked image is not perceptibly different to a human, but it's now classified as an automobile. And adversarial examples must of necessity exist for all deep neural network models. Adi Shamir proved that. It's a simple counting argument. You've got so many dimensions, you've got so many gradients that you can do ascent on, that it's inevitable that there will be adversarial examples. And what's more, the attacks are findable. What's more, they're very often transferable. And this means that in practice, you can do demos which on the face of it appear to be quite scary. Whether they are actually scary, of course, depends on your context. But can we detect them? Well, one of the things to realize is that if you're trying to tell a dog apart from a cat, you can look at adversarial examples which are near the class dog that look like a cat or near the class cat that look like a dog, but you've got to handle all sorts of other stuff as well. What about cat dogs, morphs, Or what about a dog wearing a jersey on which is a picture of a cat? What about a cartoon character? How do you deal with attempts to confuse the classifier in general, rather than just clever attempts to confuse the classifier? How do you deal with camouflage? So the idea that we had there was a taboo trap. So I don't know if many of you have been involved in raising kids, whether helping to raise siblings or raising kids or grandkids. But anyway, you train your kids to beautiful manners, and then they go off to school. And within a week, they know some words that your mother doesn't like listening to. And the fact that they break social taboos shows that they have been exposed to adversarial input. They have met wicked children in the playground. So here's the question: can we set taboos on outputs or activations during training and alarm when we see them? And the answer is yes, this works rather well. And you can even diversify this with different taboos, like in cryptography, where you've got keys. And this may have been the first interaction of cryptography with machine learning, because it enables you to produce different versions of your machine learning model that are keyed to particular makes of car, or CCTV cameras in a particular bank, for example. So the next thing that we looked at was sponge attacks. The idea Ilya had was as follows. Could you set a data center on fire by sending lots of really malicious stuff to it? Machine learning examples which were designed to defeat all the careful optimization that is done with machine learning models, where you ended up having lots of matrices that weren't sparse, for example, causing a lot more computation to be done than was planned for. Or could you even just slow the computation down, or could you drain the battery of a mobile device? And the answer is yes. And once we started doing it experimentally, we discovered a very wide range of sponge attacks on all the hardware and algorithm optimizations that machine learning people use. And we discovered completely empirically that natural language processing systems are particularly vulnerable. With machine vision systems, you tend to have a straight through pipeline. And so you can get maybe a 20% slowdown by an appropriately chosen example. But we discovered quite at random that when we put 3 Chinese characters into some Russian text, because Ilya was trying to learn Chinese, and put that into the Google Translate from Russian to English, then it caused Google Translate to run 6,000 times slower. Now, we don't know precisely what that happened. You might imagine that Google's data center in St. Petersburg calls up the data center in Hong Kong and says, hey, Fred, what the hell's going on here? But whatever's going, the fact is that machine learning pipelines are complex because they're multi-layer things that take account of phonology, syntax, semantics, and so on, using different models. And so once you realize that you can do this, you can confuse them in all sorts of ways. And the machine learning engineers appear to have forgotten that you have to design things for worst case performance rather than average case, or place limits in computation. And real systems engineers have known this stuff for decades. But the people who build machine learning systems nowadays don't think of themselves as computer scientists. They often think of themselves as data scientists or linguists or something else. And so they just don't have our culture of engineering for robustness. So another of my students, Nicolas Boucher, was inspired by this. And he looks more carefully at what you could do with coding. Now, Unicode is the standard that's used to encode Russian characters, Chinese characters, Amharic characters, all sorts of things in computer text. And Unicode games were used in the early days of phishing to obscure URLs. So can you play similar games with machine translation systems? And the answer is you can play plenty games. You can, for example, put in a Cyrillic A instead of a Roman A in an English word, and Google will completely fail to understand and recognize that. And so we played with all sorts of ways of hacking around Unicode in order to mislead machine translation systems. I mentioned homoglyphs. There are also zero with spaces, and you can use this to sabotage not just translation, but toxic content filtering. And there are many potential abuse cases. People who are doing bad things online could evade the various things that social media operators and others have put in place to stop bad things happening online. And here's an even more devious way of doing it, that Unicode also has directionality control characters, which let you swap text between left to right and right to left. About 40 years ago, I worked for a while in a typesetting system that would handle both right to left languages like Arabic and left to right languages like English. And it's really complex to try and justify text in a paragraph if some of it's going in a different direction. Say if you're embedding an English phrase in an Arabic newspaper or vice versa. And what we discovered is that we can use the directionality control characters to write an email in English, which says, please pay $1,000 to account number 123, and Google Translate turns it into Spanish as account 321. And this we found surprising because companies like Microsoft and Google and IBM have been around long enough to know that they should sanitize all inputs, right? Microsoft and IBM were already around in the days of the Morris worm, and all three companies have been around in the days of things like SQL injection attacks on websites. But why is it that their natural language processing teams just don't understand this stuff? And then we discovered that this works on source code too, because you can embed bidirectionality control characters in source code, and compilers will ignore them if they're in string literals or comments. And the result is that the compiler sees one logic and the human reviewer sees another. Now, about 10 years ago, we saw an attack where somebody had contributed some wicked code to WebKit in an attempt to get a vulnerability into devices like Android phones and iPhones, which use WebKit as a component. And we've seen such attacks again since. And if you are trying to be a contributor to an open source project who's trying to smuggle bad code past the human reviewers, then this is exactly the sort of thing that you could have used. So we responsibly disclosed the Trojan Source vulnerability to the major languages and code editors and repositories. And we got a couple of CVE numbers for them last year, and many of them fixed it, not all. This is what happens, for example, in GitHub, if you try and put in one of these adversarial examples and view it through the GitHub code viewer. And Visual Studio's fixed this. Emacs also puts out a warning. A number of languages like Rust have basically blocked attacks like this. Oracle, surprisingly enough, took the view that, well, it's not a vulnerability in Java, but in whatever editor you use to edit Java with. But then Oracle doesn't care about Java anymore, except as a source of royalty income. So this was an interesting lesson in terms of what it taught us about the various players in the computer language market and the toolchain market, and how much they really cared about their products. And other things that we learned was that the firms who'd subcontracted bug reporting to HackerOne, for example, tended to be very poor at responding to novel bug reports. And we ended up basically having to get past the subcontractor by contacting people we knew at the company behind them. But the biggest thing that we learned from this is that the big NLP models were almost entirely resistant to doing anything about this. Now, we disclosed the bad characters bug to the NLP people before we disclosed the Trojan Source bug to the computer language people. And the computer language people have mostly fixed it. But among the NLP vendors and system suppliers, only Google did anything. And what this means is that if you're relying on third-party NLP services for translation, for hate speech detection, or for general other tasks, then you remain vulnerable. So why is it that firms who do machine learning type stuff seem very reluctant to patch? What's going on here? This actually matters. Well, we got a paper on this, which has been accepted to the scored workshop in November, and it should appear in ArcSiv soon once we've fixed it up with the program committee's comments. But here's a prior view of our discussion on this. There's a number of things going on here. First is that some machine learning models are expensive to update. If you've got a large transformer model, it might take several months to retrain it and $1 million worth of electricity. But even so, you can sanitize the model inputs easily enough, and that will stop 90% of the attacks. The second is, do machine learning vendors not know that they need to do this? Well, if you're IBM or Microsoft or Google, you have people in your company who know that sanitizing attacks is a good thing, but they may not be in the machine learning teams. At one of the vendors, we heard from an inside source, the machine learning and security teams blamed each other. The machine learning people said, we don't want to deal with this bad characters vulnerability. It's boring. It's not a machine learning issue. It's a security issue. We're not going to tweak our models to do anything about it. And the security people shook their heads and said, you mean you're inhaling raw text off the internet and putting it into a production system, and you're not checking that it's not evil first? Come on, which planet are you guys on? And each are just completely blaming the other. Now, safety and security are whole systems properties. And if you're starting to incorporate machine learning components in a system that's also got lots of if statements in it, then who's going to be responsible? So here are my suggested topics for research on code versus machine learning dependability. What about the cost of an upgrade or bug fix? How different is that between the machine learning components and the conventional components of your system? And how does this work out in terms of your development environment? Are you on premises? Are you using a cloud service? Are you using a cloud service that you can't fix, so you're just entirely dependent on IBM for your toxic content filtering? If so, do you have any other options? Can you filter the stuff before you pass it to IBM? What about the time to do an upgrade or bug fix? Is your upgrade cycle once every 3 months with your big language model, or is it once a year, or is it once a week, or what is it? Next thing, culture of C coders versus culture of data scientists. If you write system level code, whether it's in C or C++ or even assembler if you're an old graybeard, then you understand that stuff springs leaks, and the leaks have got to be patched, and you've got to have a process for doing this. If you're a data scientist, your degree was in probability theory, and your MPhil was in computational linguistics, and your PhD was playing around with large transformer models, you may never have been exposed to the culture of upgrades, and you may think that upgrades are just annoying things that happen to your laptop just before you're about to give a presentation. And wouldn't it be a really good idea if we didn't bother to update stuff at all? The next thing is expectations of dependability. People expect that operating systems will be dependable, right? Blue screens of death are a bad thing, and you try not to inflict them on your customers. But if you're running a machine learning environment in which precision and relevance are up there in the 90% on a good day, and people boast about how my area under curve is better than your area under curve. In other words, where error rates of several percent are expected and just reckoned to be normal, rather than a discipline in which perfection is required because imperfections will be exploited adversarially, then things are different. A related thing is, what about expectations in the press and among the public? When we published the bad characters paper, we got 1 or 2 quiet mentions in specialist blogs. When we come out with the Trojan code disclosure, it was all over the press, because here was a vulnerability that broke basically every computer language in the observable universe. Right? Now, the machine learning attack breaks everything, but very few people were interested in it. The next thing to look at is competition and market power. You've got a small number of suppliers of very large language models. You've got a very large number of suppliers of computer languages. In fact, it was once said that most of the first 500 PhD theses written in computer science during the 1950s proposed a new computer language. We've got lots and lots of them. A related thing to this is maturity of technology and market. So here are all the different things that go together towards dependability. And as you can see, in the case of most of these factors, the dependability economics are so far weighted against dependability of machine learning. So here's some new directions. Maintenance is going to be ever more of the cost of systems as they get more complex and start to incorporate machine learning components. 30-year patching requires a more stable and powerful tool chain, but machine learning may disrupt this. Do you engineer safety and security in the machine learning model at the API or end-to-end? And how do you motivate machine learning teams to patch? And there we have it. That's my book, which was mentioned at the beginning, A Guide to Building Dependable Distributed Systems. This talk is a bit of an upgrade on the book and also covers some of the material that's already in the book. And I'm happy to take questions now if you have them.